Hey, this one is 3I, the conical pendulum. This one can get a bit tricky. So it says, consider a ball of mass M connected to a string of length L. A student holding the free end of the string whirls the ball in a horizontal circle with constant speed. The angle between the string and the vertical is theta. That's indicated right there. The student attempts to whirl the ball faster and faster in order to make the string become horizontal. No matter how fast the student whirls the ball, the string is never exactly horizontal. The very first thing they want us to do is to do a free body diagram here. So it's here on Earth, so of course there's going to be gravity. So 1, 2, 3, 4, 5 down. I'm going to label that F sub G for the force of gravity there. And then what is the other force on here? It is the tension from the string. What way does the tension point? It always points along the string, so it's got to point up in this direction. Now, how long do you make it? Because you got to make the lengths relative here. Well, this sort of takes a little bit of insight. Part of the string is going to be pulling up against gravity, and part of the string is going to be pulling it in towards the center of the circle. So where were we? 1, 2, 3, 4, 5, right there. So I am going to make my vertical part of this tension the same length as gravity there. So let's label this tension. Why is that? That actually gets to the next question, but that is all you want on your free body diagram. Now I am going to go ahead and add a little bit more. You do not want to do this. You wouldn't want to do this on the free response of a actual AP question, but it will help us see it a bit better. So let's add in here a couple things. We have this component right here. I'll call this Tx for the horizontal component of the tension. This is the one that's actually pointing towards the center of the circle. So this is the one that is the centripetal force here. Then we also have a component right here, and this is Ty. That is the vertical component of the tension, and this one is balancing gravity. So that's how I know even from the beginning that tension's got to be bigger than the force of gravity, because a component of the tension is equal to gravity there. By the way, this angle right here is what they're calling theta. So let's look at this part right here, part A, double I. They say, by discussing the specific features of your diagram, explain why the rope cannot be completely horizontal no matter how fast the ball is whirled. So there is always a force of gravity, which means, therefore, we need a Ty to cancel it out. So there's always got to be a vertical component of the tension, which means it's got to be at an angle. There can't just be a Tx. There's got to be a Ty to fight gravity, or gravity would accelerate it. Next, it says derive an equation that relates the speed v of the ball in its circle to the string length L and angle theta. So this one gets a little complicated, but let's start it. So first thing, the way we start out all of these problems here, who's the centripetal force? So Tx is the centripetal force there, so let's start off with that. We know that the sum of the forces in the x direction is equal to a centripetal force. The only force in the x direction is Tx, so that must be equal to mv squared over r. That's the beginning of it. So now let's look. Tx again right here is, if you look at what angle they gave us, this is theta, so Tx is the opposite side, so it involves the sine function there. So Tx I'm going to replace with T sine of theta, and that is equal to mv squared over r. Now I'm going to go ahead and replace r as well. So if we look here, this triangle can also double as one of not just forces, but of lengths. This length is L. So this length right here would be our radius. So just like Tx is T sine of theta, our radius would be L sine of theta to give us this side right here. So I'm also going to replace the r with L sine of theta there. Now, a lot of people might get this far and then get stuck. So the next thing is we're going to have to actually substitute something, because we can only have L and theta in our answers. No mass, no tension. So we're going to have to sub for one of those, which means we're going to need another equation for tension and mass. And that means we need another source. So the best source of that is the y. We know that the sum of the forces in the y direction is equal to mass times acceleration in the y direction, which is 0. So that means the sum of the forces have to be equal to 0. So we know that we've got the tension in the y up minus the force of gravity down is equal to 0. And if I solve that, then move it to the other side, tension in the y is equal to the force of gravity. What's tension in the y equal to? Well, you can see here that it is the adjacent side to the angle. So it is going to be the cosine function. So this is going to be t cosine of theta, and force of gravity is just simply mg. I'm going to do one more step and then substitute over here. I'm going to solve for t, so I can substitute it over here. So t is equal to mg over cosine of theta. Now I can take this and substitute it in right over there. So it's taking all of this and plugging it in for t here, we get mg, can you see that? Yeah, I guess so, over cosine of theta. All of that was t, so that's going to be multiplied by sine of theta, and that is equal to this whole side over here, mv squared over L sine of theta. You can see how much of a mess this is. Let me switch out, that's a little hard to see. One thing is that the masses cancel, so the mass is there and there, and I can simplify these two. Sine divided by cosine is tangent, so we get g tangent of theta is equal to v squared over L sine of theta. So now we're almost there. I'm going to multiply this up to the other side so that I get g times L times tangent of theta times sine of theta. All of that would equal v squared, so I'm going to go ahead and square root all of it, and that's equal to v. Man, that's a lot. That's a hard one. So the last part here is asking you to make the same argument you did here, but looking at your equation. And this is a little bit harder to see too, because people don't realize the effects of tangent as much. But for this to be horizontal, the angle would have to be 90 degrees, all the way out here. So your sine would be fine. Sine of 90 is 1. But if you know how tangent works, as the angle goes to 90, tangent goes to infinity. So it's basically saying you would have to spin it infinitely fast in order to, and that kind of makes sense. The faster and faster you spin it, then the tension's got to be so big that that little bit to fight gravity would be a small fraction of it.